Hello, chemistry people. Welcome to our topic 6 revision lecture. I'm in a different room, so I'm sorry if the sound is a little bit different to how it normally is, but I'm just in a slightly different office in the school. So let's get started. As always, by looking at the subject guide. So the subject guide, we start with a discussion of collision theory, then we go into how we express rate of reaction, how we measure rate of reaction, and talking about activation energy, specifically about catalysts. We talk about kinetic theory a little bit. We analyse graphical and numerical data, explaining effects of those guys, making Maxwell Boltzmann. This investigation needs to be done in the lab, so I'm not going to be discussing it in this video. And looking at energy profiles. Now, energy profiles also massively come up in topic 5, which is energetics and thermochem. So I'm not going to go into massive amounts of detail there. So let's continue on by talking about collision theory. Now, people in my class will know, but this is one of the few things that I ask students to be able to do from memory. So there are 3 components to the collision theory. In order for a chemical reaction to occur, my particles need to collide with sufficient energy in the correct orientation. Now, how we are defining sufficient is that the energy of that collision has to be greater than or equal to the activation energy. And the other term you might hear is, instead of orientation, is reaction geometry. Same thing. Okay. If you are after more detail on these, on anything in this topic, can I suggest the other kinetics video I've made? This is really more of a summary rather than a teaching aid. So the IB defines rate of reaction as the change in the concentration of either reactants or the change in the concentration of product over time. Now, the IB needs you to know that it is concentration. So in the mark schemes, they will often specify that you need to include the word concentration. So by definition, reaction rate is the change in either the concentration of reactants or products over time. Okay, when we follow a reaction, we can't exactly ask the particles what they're up to. So we need to measure a change in something that we can then link to a change in the concentration. So I can measure a change in mass if there is something like carbon dioxide gas being evolved. I can measure a change in volume if it's a lighter gas like hydrogen or oxygen. I can measure pH if there is an acid or a hydroxide as either a reactant or a product. So if you've got a pH probe and you stick that in, if your reaction is either consuming acid or making acid, we can monitor the reaction from that. In certain circumstances, you can measure colour if you're using a colorimeter. That works best for things with transition metals and also some organics. So, for example, if you're doing something with chlorophyll, you should be able to measure a reaction rate with chlorophyll, like breakdown of chlorophyll, using a colorimeter. All of these can be, like the stoichiometry can be done to turn those into a change in concentration. But when we follow a reaction, we most of the time can't measure the concentration directly. We need to go with something that is more measurable as an initial step, and then do the maths to take it to the change in concentration. So when we analyze graphs, so let's say that I've got a conical flask here with solid calcium carbonate and aqueous HCl. Those two form water, calcium chloride, and CO2 gas. So this is making CO2 gas, which, because it's heavier than air, lead to a decrease in mass. So when this reaction first at time equals 0, it's going to have the highest possible mass that it will have. Then, as this reaction occurs, it will initially lose mass quite quickly, but then as it continues to react, this reaction is consuming the HCl, which decreases the concentration of the HCl, which means it's going to react more and more slowly until I reach the end point of that reaction. So when I analyze this graph, if you've got it in your computer, it's easier, but even if you've got a drawn graph, you should be able to draw tangents to this curve and then work out the gradients of these tangents using the change in y over the change in x. So y2 minus y1 over x2 minus x1. If there is ever a question like this on an exam, they do provide a range of numbers, not a massive range, but enough of a range that if you draw your line in a slightly different way or you take slightly different points, there is enough room there for there's a bit of wiggle room there on the numerical answers. So these graphs, you should be able to construct them. So if you are given a data set, you should be able to draw those points and then draw this curve. And then from there, draw tangents to that curve and work out the gradient of those tangents. You don't need to ever differentiate. So you don't need to differentiate if you're given a formula for a line, you don't need to differentiate it to work out like an instantaneous gradient. Okay, activation energy. Activation energy as a concept is that chemical reactions require a certain amount of energy to get them started, to activate them. And the amount of that activation energy varies depending on the circumstances. So some reactions require more activation energy than others. So the activation energy is just the initial spark. So the example I always give, because it's one that most of us are familiar with, if you've ever seen a gas stove or a gas barbecue or a gas oven, we know that that reaction releases a lot of energy, but I still have to give it a spark or a match to get it started. So I still need to supply a little bit of energy, that initial spark, in order to get my reaction working. This is why activation energy is tied into that idea of sufficient energy. So if my collision is happening with sufficient energy, with energy greater than the activation energy, my molecules are able to break apart and reform into the products. Okay, so I would assume that we all know, just from having been in kitchens at some point in our lives, that if I cook something on a high flame, it cooks faster than if I cook it on a low flame. Just logically, if I'm boiling a pot of water, it happens faster on a high flame than a low flame. Why does that happen? Let's go back to our 3 initial points. So, in order for a reaction to occur, things need to collide with sufficient energy. In the correct orientation. And I'm going to grab a copy of this because I'm going to be coming back to these points again. Copy. Okay, so when I'm looking at the effects of temperature, temperature affects in 2 ways. So temperature is just looking at the kinetic energy of my particles. So at a high temperature, my particles are moving faster than they are at a low temperature. We come back to this later when we look at Maxwell Boltzmann distributions in about a couple of minutes. But temperature is a measure of the kinetic energy of my particles. So at a high temperature, so high temp, that is effectively the same as saying high kinetic energy, which means I am affecting this sufficient energy. The other thing I'm doing, and it's to a lesser extent, I am also increasing the collision frequency. And remember, all of these are, when we're talking about rate of reaction, we're not talking about the number of collisions. We're talking about the frequency of collisions. How many collisions per unit time? Again, that is a point of terminology that the IB can sometimes be a bit finicky about. So make sure that you are talking about collision frequency. So when I increase the temperature, the primary way in which that increases reaction rate is by supplying more energy. However, it also has an effect on the collision frequency. So this is the most important, and this is there a little bit, but not as important. Okay. So pressure and concentration. I've linked these two because, oh, why? Why did you shrink? Oh, that's weird. Okay, so sorry about that. I don't know what's gone on. So pressure and concentration. Pressure is for gases, but concentration is for stuff that's aqueous. Effectively, we're talking about the number of particles per volume in both cases. So that's why I've linked them. If I have more particles in a space, it makes it more likely that they will collide. It affects the rate of collision. It doesn't alter the energy, so I can have 1 mole per DM3 hydrochloric acid at 25 degrees. I can also have 5 mole per DM3 hydrochloric acid at 25 degrees. If I have the same temperature, I'm dealing with the same energies. It's only once I start messing with temperature that I'm changing that sufficient energy. I'm also not changing the proportion of molecules that collide in the correct orientation. So my particles are colliding more frequently. The energy with which they're colliding isn't changing, and the orientation in which those collisions occur isn't changing. So pressure and concentration, it's all about that rate of collision. And remember, we're talking about rates. So it's either frequency of collisions or rate of collisions. Just making sure you use that exact terminology so that the IB can't take marks off you. So particle size. So remember, collide, energy, orientation. So particle size is again all about collision frequency. So if you are a biology student as well, you talk about surface area to volume ratios. That's what this is about. The larger our surface area to volume ratio is, so particle size is all about the surface area to volume ratio. So if I've got a high surface area, it means there are more of those solid, so particle size is all about solids in the same way pressures were about gases and concentrations were about liquids, aqueuses, sorry. Particle size is all about solids. So if I increase my surface area, there is going to be more particles sort of open to be collided with. So if I increase my surface area, there are more particles that are open to be collided with. If I increase the size of my particles, I am in effect decreasing the available surface area. So a large particle size means a comparatively small surface area. It's only once, so sorry, those two things work opposite to each other. So think about like cooking potatoes or any vegetable. If you cut it up small, it cooks faster. More of that surface area is exposed. Okay, so particle size is all about collision frequency. So let's talk about Maxwell-Boltzmann distributions. Get used to drawing these. Like odds are there will be either a Maxwell-Boltzmann distribution, or it'd be nice if I could draw a straight line. That's not straight, but it's closer. You will either be asked to draw a Maxwell-Boltzmann distribution or a reaction profile. Like basically you can put money on that one. So along this, I'm going to call it the x-axis. This can be labelled as energy. It can also be labelled as kinetic energy. And along this y-axis, my apologies, this is either like number of particles or frequency of particles. And sorry, I mean frequency in terms of number of, not frequency in terms of waves. So Maxwell-Boltzmann distribution, the points you need to know. It starts at 0, 0. You have 0 particles with 0 kinetic energy. At a cold temperature, it increases quickly and it hits a curve and then it tails off. Okay, so 1 point, so it's got to be down in this 0, 0. It hits the top of our curve and it tails off. So it does not touch axis. So sometimes you will be asked to draw the one curve, the one sample at 2 temperatures. So let's do green for our higher temperature. what the IB will want is a peak that is lower and further to the right. So again, it starts at 0, 0, and again, it tails off. But the peak of this curve is lower and to the right of this peak. The area under those curves is the number of particles. So this green curve has the same number of particles as my purple curve, but they are distributed around a different mean. So what this means for our reaction rate, what if this is our activation energy? My purple curve has a much lower area under it, much fewer particles compared to my green curve. So area, be good if I could spell, area under curve equals number of particles. So my green curve has a much greater number of particles that are greater than or equal to that activation energy. What does adding a catalyst look like? Adding a catalyst looks like shifting my activation energy down. Have I talked about catalysts? Oh, I skipped talking about catalysts. Well, that wasn't very clever of me. Okay, I'm going to have to do like a literal side note here about catalysts. So this terminology is important, particularly at HL. You will get marked down if you do not hit one particular part of this. So you probably had it explained to you in the past that catalysts decrease activation energy. So catalysts work by decreasing the activation energy and that they are not chemically changed. So catalysts decrease activation energy and are not chemically changed by the reaction that they're facilitating. There's one super important thing that we need to add to this first point. Catalysts decrease activation energy by providing an alternate reaction pathway. Now, for HL people, we will talk about rate equations and how catalysts get involved with them, but it is a different reaction. So, for example, this is going to make sense to people from Melbourne, but will make no sense to anybody else. If I'm going to lawn, like now in winter, it's probably not so bad. But if I'm heading down over New Year's where you've got like Falls Festival and stuff like that, you would be silly to try and drive along the Great Ocean Road. So driving from Melbourne to Lorne along the Great Ocean Road, that's slow. But there is a path sort of up through Dean's Marsh that is a lot faster. It is an alternate pathway that is easier. So it's a shortcut. That's what the catalysts do. It is not the same reaction. It is a different reaction than the uncatalyzed, but it requires lower energy. Okay, now that we've done that little side, so what does that mean in terms of what a Maxwell-Boltzmann distribution looks like? When I've got the activation energy with my catalyst, the proportion of particles that can react is this new part plus all of the ones that were already able to react. The activation energy with a catalyst is this lower line. Make sure you're using some sort of notification, annotation, I should say, to show EA-cat versus the uncatalyzed reaction. Now, reaction profiles, we've talked about them with the energetics topic, but let's quickly just draw up an endo and an exo. So in an endothermic reaction, my reactants have low energy and my products have high energy. And in an exothermic, it's the other way around. Okay, so I'm going to draw my uncatalyzed reaction in purple. So, and I know I've exaggerated that. So this here is going to be my delta H, and this guy here is my activation energy. I'm just going to move this slightly to the side here. So this is going to be my activation energy. However, when I use a catalyst, what it does is it changes, it decreases that activation energy. So that means that the EA-cat is that green line. So it's still quite a lot of activation energy, but it is less than it was before. Let's do the same colouring and look at an exothermic reaction. So, no, I'm going to make that a bit more exaggerated. Always exaggerate these. It's going to be easier for you to see and easier for them to be marked. So my activation energy is from my reactants to the top of my hill. And my delta H is this guy. My delta H is not changed by the presence or absence of a catalyst. That delta H is independent of whether or not I'm using a catalyst. However, if I do my exo with a catalyst, it could, so EA-cat, that looks like rat. C-A-T, yes. So when I use a catalyst, that delta H remains the same. It just decreases that delta H. All right, so let's go back and look at our subject guide. We talked about collisions with sufficient energy in the correct orientation. We talked about the change in reaction, the change in concentration. We talked about how we can monitor changes in reaction. We talked about what activation energy is, and we talked about catalysts. We talked about kinetic energy, and its links to temperature. We did this briefly, but this is something that I go into a bit more detail in the other kinetics video. Plus, there's also all sorts of textbook and IB questions online. We've talked about temperature, pressure concentration, and particle size on rate of reaction. We looked at Maxwell Boltzmann, including the effect of a catalyst. That's something you've done in the lab, and we sketched energy profiles. I talked about tangents and interpretation of graphs. That is a practice thing. Okay, so that is the end of our little summary lecture on the SL Kinetics course. Thank you so much for your time and have a fantastic rest of your day. Bye.